So today we are going to start with a new module, memory management. Some part of this memory management you might have read in computer organization and architecture, a part of virtual memory you must have read. However, we'll read the memory management in operating system point of view. We'll read the memory management in operating system point of view. These virtual memory part, almost many part of these are same as you have read in your computer architecture. So anyway, we are going to start from the beginning itself. So today's topic of discussion is the memory management. As you know that in your computer system, besides the processes which are being executed by the processor, the next important thing in your computer is the memory. Why it is there? Because every instruction that is going to be executed has to be stored in memory before getting executed. Everything has to be stored in memory before getting executed, right? So main memory and registers are only storage. CPU can access them directly. You may have secondary devices, hard disks, floppy drive, pen drive. CPU don't have direct access to them. So data is transferred from the CPU from the other devices to the memory and or to the registers, and from which the processor. So the data that are being stored in memory or the CPU registers can be accessed directly by the CPU. They can be accessed directly by the CPU. Correct? So if your data is there in any other secondary storage, those are not being accessed directly, rather those data are transferred to memory and then it is being accessed. So program or data must be brought from the disk into the memory and placed within a process for it to be run. Correct? So the program that you say, the program is nothing but it may be there in the disk. When you brought into memory, we said is a process, and then it is given for execution. How to execute, how to create processes, operation on processes we have read. But now we'll read about how it is being stored in the memory. Register access one CPU clock or less to access this data. Memory unit only sees a stream of addresses for read request or address for data and write request. So memory unit will say that whether we are writing into the memory or reading data from the memory. Only two operations we do in the memory. Either we are reading from the memory or writing data into the memory. For both these operations, we require an address. If we want to store, suppose I write a equals to 5. We are writing in the data. To write the data 5 into the A must have a memory location to which you are writing the data. So you must know the address where the A is stored. If I give printf %da, so I must know the address of A so that I will get the value of A from there. So we need for any read or write operation, I need the address. I need the address for the same. Correct? So main memory can take many cycles, sometimes causing a stall that you might have read in architecture. For the time being, we remove it. Cache, for the time being, we are not going for this cache memory, because cache memory you have already discussed in computer organization architecture. That is not a part of your operating system. We are not going to discuss that. So cache sits between main memory and CPU registers that you know to make the process faster. Now each process, this line is important. Each process has a separate memory space. Each process has a separate memory space. It says that, suppose this is your main memory. In main memory, one part where your operating system resides. And the rest of the part, there might be multiple programs residing over here. Multiple programs might be executing over here. But every program has a separate memory space. They have separate memory space. Hello. Each process has separate memory space. Correct? And protection of memory space is required to ensure correct operation. So that means if here the particular process is executed, suppose process 1 is over here, it is executing, a set of addresses is given for this process. The addresses, if I want to do some read and write operation, the addresses must be generated within this range. Correct? This is the process, right? If I want to access the process for any read or write operation, then I must generate an address between a fixed range for correct operation. So you can see over here. Here the suppose operating system either in the upper memory or lower memory area. Here in the upper memory area, operating system is there. There are multiple number of processes. This process is starting with this address. Second process is starting with this address. The third process is starting with this address. Correct? The process 2, suppose this is process 1, this is process 2, and this is let process 3. Correct? In the process 2 starts from this address to this address. So this is the range of addresses. This is the range of addresses given to the process 2. Starting from 300040. So this starting address is stored in a register called base register. The starting address of a process stored in a register called base register, and the limit is stored in a register called limit register. So this plus limit gives you this boundary. Correct? This gives you that boundary. So this not this boundary actually. This is plus. This gives you some values. So that means up to this only the process 2 can exist. After that it may be vacant. Here process 3 is there. It may be vacant or something. Other data might be present. So a process will reside in the memory, and we are keeping two informations over here. Whenever a process resides in the memory, two information has to be kept. What is its starting location and what is the limit or span. Suppose it is from 1000 to 1500. That means base address is 1000, limit is 500. If it is from 3000 to 5000, so starting is 3000, limit is 2000. So limit is stored in a register called limit register. The starting address is stored in a register called base register. So these two must be remembered. Must be understood.
For all the process, there will be a base and limit.
Yes. For every process, there is a base register and limit register. For every process, suppose I have 100 processes. So every process has a base and limit. So a pair of base and limit registers define the logical address space. Now question there, what is a logical address space? It says that there are actually two different addresses. One is called the logical address, another is called the physical address. The actual address in the memory is called the physical address, and the address generated by the processor is known as the logical address. Try to understand. Suppose this address may be a physical address. But logical address says the address generated by the processor. The processor may not generate this number. It generates some other number which has to be converted to the physical address for processing. Correct? Now you might be asking that why we have two different addresses. Processor could have given directly the logical address. It says that, suppose I'll give an example in your exam hall. How the roll numbers are written in your SIC numbers or registration number is given on your exam halls. In your exam hall, you will find the first roll number, first SIC number is written completely. Right? SIC 00127, like that the number is written. Suppose the first one is 07 SIC with the number 100. For the next sheet onwards, we are not writing the entire SIC number, rather only writing 2, 3, 4, 5 like that. Why it is there? These 2 and 3 are relative to the base. These are relative to the base. If the first roll number is 102, 102, 07, 001, the next roll number is written 002. Is actually 002 with reference to the base one. Correct? So here also the processor suppose generates 7. The 7 is actually a logical address, but what is the physical address? The base address plus this will give you the actual address. Correct? So we have two different addresses over here. The actual address in the main memory is called the physical address. Address generated by the processor is known as the logical address. The logical address has to be converted to physical address for processing. Correct? So the base register holds the smallest legal physical address. So this is the smallest legal physical. That means if logical address is 0, that means I am referring the first location. If it is 1, then 300041. If it is 7, then 300047. So this 7 what you are generating is a logical address. 300047 is the physical address. So smallest physical address is being stored in the base register. The limit register specifies the size of the range. What is the range over here? The range is this one. We can have the physical logical address can be generated maximum up to this. So limit register specifies the size of the range. So CPU must check every memory access generated in user mode to be sure it is between base and limit of that user. So what is a valid address for this processor process 2? What is a valid address for process 2? Can anyone answer? What is the valid address for process 2?
The base register.
Starting from 30040 to, so that means any address of this range is a valid. It should not exceed that range. It should not, when the logical address should not exceed this and the physical address should not exceed this. Because this plus this gives you the, this plus 7 gives you the physical address. This plus 20 will give you the physical address. Correct? So it should not be more than this limit. Let us see over here. What is the formula it uses for? Look it carefully. This is very important. The memory space can be protected by using the following hardware. There is a hardware logic for the same. What is that? CPU generates address. Can you tell me which address it is? CPU generates address over here. Which address?
Logical address.
Yes, it is a logical address. So address generated by the processor is logical address. It is checked with the base address. The logical address is checked with this base address. If it is greater, it is actually added with this base address. Correct? Now, from the base address, the address generated by the processor must be greater than this from the base address actually. And if it is greater, it must be less than the base plus limit. It is greater than base and less than base plus limit. It is greater than base, greater than this, but less than this. Where it is? So this address, now it is saying only address, logical address I will tell you. So this address is greater than base and less than limit. This is not, I am not talking about the logical over here, only address. The address must be greater than base and less than base plus limit. If it is greater than base and less than base plus limit, it is valid address. If it is not greater than base, then it is an error, trap. the operating system monitor, there is an addressing error. And if it is not less than base plus limit, then also it is error. So if it is less than base or greater than this base plus limit, then it is a error. So the address, this address must be greater than base and less than base plus limit. Understood? Who will provide this address? The base and limit registers can be loaded only by the operating system. The value of this base and limit register, who will give? The operating system will give. Is it understood? This diagram is understood?
Yes, sir.
So binding is a mapping from one address space to another. Address binding. Address binding says that mapping from one address space to another. The processes wait on disk ready to be brought into the memory for execution from input queue. So processes, before that it was program which was there on the disk is brought to the memory for execution. Addresses represents in different ways at different stages of program. What are those? We write the source code actually. The source code addresses usually symbolic. What you write? A is equal to 10 or count, or we write number of students. These are symbolic in nature. We write suppose A equals to 10. So A is not actually the address, A is a symbol for a particular location, right? So source code addresses are symbolic. Compiled code addresses, when it is being compiled, right? Compiled code addresses bind to relocate addresses. So where it will be stored, the compiled code address will bind it. So whether it will be 20 bytes from the beginning of this memory or 30 bytes from the beginning of the module. So exact location from where it to start, that is need to be given at the time of compilation. So there is a need of this variable, the symbol with this address, and that is known as the binding. Compiled code addresses bind to relocatable addresses. Relocatable addresses. Linker or loader will bind relocatable addresses to absolute addresses. Now, at the time of when the linker or loader will work, at that time it will be will bind the relocatable addresses to the absolute addresses. Absolute address is the actual address or physical address in the memory. Relocatable addresses which can be changed at the at the runtime or the time of date. For example, this is the physical address or the absolute address we can see. So linker or loader will bind relocatable addresses to absolute addresses. So each binding maps one address space to another. If you have 20 variables, all those 20 variables need to be bind to your memory locations, relocatable addresses. So every variable, every functions that you are defining, each one need to be bind to the relocatable addresses. Just look over here. So this program, we have written the program, that is the source program which is going to be executed. This is the source program, right? The source program over here. The source program is compiled, then it goes to the assembler for execution. As you know that the program must be compiled, then it goes to assembler, then the machine code is generated. Correct? Source code, then to the compiler, then to the assembler, and the machine code is generated. Correct? And then your object module is generated actually. That is called the object code. So from source code to object code, we use compiler or an assembler so that we will get the object module. Then the object module, you goes through this linkage editor. Linkage editor means one program may have linked to other programs, other libraries, other programs. So object module linkage editor will other object modules, it will link it. Right? Then it goes to the load module. The load module, it goes to the through the loader, right? At the time of loading, it will load those system libraries or other dynamically loaded libraries. And then it goes for the binary image is generated, which will go for execution. Out of this total flow, this is the compile time. The source code to object code conversion. This is your compile time. This is your compiler or assembler will work. This time is called the compile time. Then it goes to the linker and loader. This time is called the load time. The object module goes through the linkers and loader for linking different modules and system libraries. Those are called the load time. When the binary image is being created and it is for execution, then it is called the execution time. So three different times are associated while executing a program. First, when the program is compiled and assembled, this time is called compile time. And when the linker and loader are being used over here, linkers and loaders for linking to the other modules and loading the system libraries, dynamical libraries, those are load time. Then the binary image is created and executed, though that's called the execution time. So address binding of instruction and data to memory addresses can happen on any three different stages. What are those? So this address binding, what you have read over here, this can be done at compile time, this can be done at load time, this can also be done at the execution time. Suppose you have written, for example, I am giving, you have written if A is equal to 5, you call X program, else you call Y program. Try to understand. If A is equal to 5, call X program, else called Y program. It is sure that X and Y will not be called definitely both cannot be called, either X or Y. It is not required that both X and Y to be loaded at the runtime. So at the runtime, while executing the program, that time only we will evaluate the value of A and will decide whether the procedure X or the procedure Y will be called. So that means those code will be loaded dynamically. At the runtime, it will be loaded. It will be decided at the runtime. Correct? So suppose your program, a particular program you want to install on your machine. So depending on your machine, so when you will try to run, it will find out what processor it is. So looking into your processor, your program or your coding will be changed. So compile time, if the memory location known a priori, if it is known before, if the memory location known before, what time? Compile time. If memory location known a priori, absolute code can be generated. Most recompile code if starting location change. If I know the absolute code, if the memory location is known a priori, if I know that in which location it will be stored, then absolute code can be generated. But once it is changed, we have to recompile it. So now the program is being stored in a location. If I take out and load it in another location, then I have to recompile the code because binding has to be taken place again. Correct? Similarly, for the load time, it must generate the relocatable code. As I said, after binding, the relocatable, see over here, where I have written, the symbolic codes bind to relocatable addresses. So load time must generate relocatable code if memory location is not known at compile time. If it is known at compile time, then we generate the absolute code. If it is not known at the compile time, we generate the relocatable code. So final binding is delayed until load time. So is it understood? So if the program, if the memory location is known a priori or known before, we say that code is called the absolute code. If the address is not known and decided at the compile time. It's not decided at the compile time, we said is a relocatable code. Execution time says binding delayed until run time if the process can be moved during its execution from one memory segment to another. Suppose during execution, I need to move the program from one segment to another segment. Then the binding is delayed. Binding is delayed over there. That we say that is done in the execution time. Correct? So for all these, we need a particular map between the base and limit registers. What we need? So if the program is stored in some other location, the base address should be changed. Limit address may not change. But if the program at the runtime, a particular new module is being added, my limit register may need to be changed at that time. Correct? So while executing the program, we must know the base address, base register content for every process, base and limit register content. If we know the address, then it is absolute code that can be generated at the compile time. If it is not known, it can be generated, which says a relocatable code at load time, and at the execution time, if you change the program to different modules, then it is done at the execution time. Is that clear? Okay. So now we'll go for logical address space and physical address space. The logical address, as I said, generated by the CPU, and physical address space is the actual address in the main memory is called the physical address, as I said. Correct? It is generated by the CPU. Also referred to as virtual address, or always we do not say all virtual address, rather in the virtual memory concept we say is a virtual address, but usually the address generated by the CPU is known as the logical address, and actual address in the memory is called the physical address. Correct? So the concept of logical address space that is bound to separate the physical address space is central to proper memory management. So we have two addresses over here, logical and physical. I hope you understood this logical and physical. Physical address is the actual address in the main memory. Logical address is generated by the CPU. Logical addresses are the same. Logical addresses are the same in compile time and load time. Load time address binding schemes. The logical and physical addresses differ in execution time address binding scheme. I'll tell you those. First you would understand that what is a logical address space and physical address space. Set of all logical addresses generated by a program is known as logical address space. Just look into this example. In this example, what is the logical address space? We can generate an address starting from 0 to 120899. The set of those addresses are logical address space. Those are logical address space. Set of all logical addresses generated by the program. The set of all physical addresses corresponding to these logical addresses are called physical address space. So those, suppose from 5000 to 7000 is their actual memory addresses, then those are called physical address space. Is it understood, or I'll repeat it again? Is that understood? Suppose this is the memory. One program is loaded over here, process is loaded. The starting address is 1000 to, this is 1000 to suppose 3000. Correct? 1000 to 3000 the address. 1000 to 3000. So how much, what is the logical address over here? Logical address is from 0 to 299. Sorry, the range is how much? Range is 2000. 1000 to 3000 means it is 2000. So address can be generated from 0 to 1999. This is the range of addresses that can be generated by the processor. 1199. Sorry, 199 1999. Correct. So this is the set of addresses generated by the processor, which is a logical address. What is the physical address space over? This is logical address space. What is the physical address space? Physical address space is 1000 and 3000, 1000 to 3000. Physical address space is 1000 to 3000. Logical address space is this. So set of addresses, this set of addresses generated by the CPU. This is the set of addresses actually corresponding to these logical addresses are called physical address space. Is it understood? Hello? Is it understood?
Yes, sir.
So look over here. The CPU generates the logical address. Suppose 346 is generated, right? The 346 is added with this relocation register, right? Relocation register. So this address, this 14,000 is added with 346 to get this physical address. Is that clear? The logical address is 346. Relocation register contains 14,000. So physical address is 14346. Why say that this is we say relocation register over here? Because actually this is the base register, but we say relocation because this gives you another address. Actually this relocation register is also a base register. The base register is actually the relocation register. The base register. Correct? This is the base register. So memory management unit is a hardware device that maps the virtual to physical address. So processor generates logical address. Actual address is physical address. Who will convert this? The memory management unit will convert the logical address to physical address. Memory management unit is responsible for converting logical address to physical address. Memory management unit, in memory management unit scheme, the value in the relocation register is added to every address generated by the user process at the time it is sent to the memory. Correct? So the base register is now called relocation register. The base register is now called relocation register. The user program deals with logical addresses. It never sees the real physical addresses. User program deals with only what? Logical addresses. So execution time binding occurs when reference is made to location in memory, logical address bound to physical address. So from here we'll remember the address generated by the processor is logical address, which need to be converted to actual address in the main memory physical address. Who converts is the memory management unit. Memory management unit is responsible for converting logical to physical address. Here the base register is called relocation register. Here the base register is called relocation register. So now we have two concepts over here, dynamic loading and dynamic linking. Dynamic loading and dynamic linking. Dynamic loading means, in short, you remember, the loading is postponed till the runtime. So we may not require to load all the modules. We may not require to load all the modules before at the time of execution. As the example I have given, if A is equal to 5, procedure X, else call procedure Y. I may not require both X and Y procedure to be loaded. So with dynamic loading, a routine is not loaded until it is called. So loading is postponed until there is an explicit call to the particular routine. So all routines are kept on the disk in relocatable load format. So address computation is done, but it will not be loaded to the memory. Only main is loaded into the memory and is executed. That means main function may be calling many other programs. Only the main, that program, the main program will be loaded to the memory. When routine needs to call another routine, first it checks the called routine has been loaded into memory or not, whether it is there or not. If the called routine is not loaded, the relocatable linking loader is called and load the desired routine and update the program's address table. After that, control is passed to newly loaded routine. So what it does? So whenever a call is made, it will check that whether it is loaded or not. If it is not loaded, then both dynamic linking and loading is being called and it will be loaded to the memory. New address space is being generated. What is the advantages that you get from a dynamic loading? What advantages you will get from dynamic loading if you do this? Unnecessary loading of programs in the memory will not occur. I may not require all the programs to be loaded. I only load those programs or link those programs which are in need, currently required. Correct? So advantages is that better memory space utilization and unused space is never loaded. Unused space is never loaded. If there is no error, then error space is never loaded. I may have 10 procedures in my program, but I may not be requiring all these 10 procedures to be called. So whenever at the time of calling only, I will decide that whether it will be loaded or not. So no special support from operating system is needed, can be implemented through program design. I just need if else condition kind of thing, and from this only I can check that whether the loading can be postponed dynamically by runtime or not. Is it understood? Exactly same way we have dynamic linking. Dynamic linking says that the linking will be postponed unless it is not being required, unless it is not being executed. So at the runtime, it will be decided whether a module will be linked or not, a library will be linked or not. So this dynamic, there are two linking. One is static linking, another is dynamic linking. Static linking means fixed system library and program code combined by loader into binary program image. I will write that in this location you store, in this memory location you store. This is static link. But when you write a program, we do not specify memory location. We write a equals to 10. A must be a variable somewhere. So dynamic linking. So dynamic linking, the linking is postponed until execution time. So nowadays, all those high level programming that you are using, all uses dynamic linking and loading. But time was there when people used to write programs in low level languages, they need to mention that in which memory location it has to be stored. So if your address, a physical address, you are specifying this as static linking. Dynamic linking uses a small piece of code called stop. Small piece of code called stop used to locate appropriate memory resident library routine or how to load the library if it is not present already. So dynamic linking uses what? A small piece of code called stop. A stop is used to locate the appropriate memory resident library whenever how to load and it is being stored in that stop itself. So this stop replaces itself with the address of the routine and executes the routine. So here only you remember dynamic linking is Linking, this line is important. Linking is postponed until execution time. A small code stub is used um, for finding the library and loading it. Operating system checks if routine is in process memory address or not. If not, the address space added to the address. So next time when it is run, it will get the address. So dynamic linking is particularly used for libraries, because there might be this library may be required for multiple times. Once it is linked, it can be accessed multiple times. Is the dynamic linking and loading understood? Hello? Is the dynamic linking and loading understood or not? Or any doubt?
No, sir.
Yes, sir.
One more concept we will discuss over here, the swapping. You know that the program has to be brought to the memory for operation so that it can be processed. But sometimes the program, suppose this program I have loaded, these are the processes over here or programs over here in the backstored. That means on the disk it is there, correct? I load it into the over here into the memory. This is loaded to the memory, and whenever required, I will also take it out to the disk. Correct? Why it is being taken out? Two reasons. One reason is that sufficient memory space is not available. Then some data has to be taken out to the backing store. Second one, it may be those are not required presently, and we are not bringing to the main memory. If the main memory is full, I may have to take some part of the program. Second one, if that part is not required, will not load to the memory, right? So bringing the data, this process continuously takes place. You must have read in virtual memory as well in architecture. Let us take an example. Suppose I'll say I want to execute a game in my machine. I want to execute a game of 4 GB. But in my laptop or my computer supports only 2 GB of RAM. The first question is that can I execute or not? In 2 GB RAM, can I execute a 3 GB program or not? The answer is yes if I go for virtual memory concepts. The program will be stored in disk. A part of the program will be brought to the memory. It will execute. Whenever the next part is required, the previous part will be transferred to the disk and a new part will be brought to the memory. This process is called swapping. Taking the data from disk to memory is called swap in. Taking out the data from memory to disk is called swap out. So you must have marked that if a game has multiple number of stages, you are actually not using all the 5 stages or 10 stages at a time. When you clear stage 1, then only you will go to stage 2. So why to load the entire thing in the memory? So what it does, it first loads the stage 1 program. The moment you clear the stage 1, then stage 1 will be taken out to the disk, and the new program may be another part of the program which is required. Maybe stage 2 will be brought to the memory. Correct? So that process is known as the swap in, swap out. Even if the memory space is there, I am not bringing both the entire program into the memory. The part which is required, I am just bringing it. Whenever not required, or taking out the swap in and swap out. Correct? This process is known as swapping. A process can be swapped temporarily out of memory to backing store and then brought back to the memory for continuous execution. Correct? So what backing store, you know that it's a fast disk actually. This swap in, swap out is also known as roll in, roll out. The swap in is also known as roll in. This is also called roll in. This is called roll in and this is called roll out. Swap out is also called roll out. Roll out. Correct. So major part of swap time is transfer time. Total transfer time is directly proportional to the amount of memory swap. So system maintains a ready queue of ready to run processes which have memory images on the disk. Is the swapping understood? Here the important, what is swapping? What are roll in and roll out, or swap in and swap out?
The memory images mean?
Hello?
Yes, sir. Sir, memory images means?
Memory images on the disk means if you have a, you must have the data that from what is the starting location, from which, from where it is being stored, what is the length of the program, all these informations must have been kept, and in which memory location it has been loaded, all these information has to be there. That means if a process, suppose a process is over here, I want to load it into the memory, then I must know that in which address it has to be loaded and what is my limit register. That information has to be. So memory information must be known for that process while it is there in the vacuum store. Hello? Is it understood?
Yes, sir.
So what the system maintains, system maintains a ready queue of ready to run processes. There might be multiple processes. Suppose here you have a program you are executing, they may have a number of parts process over here. So now what you have, each one where to be loaded, in which location it is there, that memory, those information has to be kept. Those are the images. So next class I will continue with this swapping itself. I'll go with this swapping. We take the 10 minutes.